So we have heat capacities for constant volume systems and heat capacities for constant pressure systems. How are they related? Well, that relationship depends on what type of state of matter you're dealing with. All right? And these relationships, they depend on the state of matter, and this is going to tie back to stuff that you learned about back in chapter 5 when you dealt with the differences between incompressible and compressible fluids. So let's start with the incompressible materials, which included solids and liquids. Okay? For solids and liquids, let's consider, go back to the definition of enthalpy, which was the internal energy, change in internal energy, plus P delta V hat, right? Because we're dealing with specific stuff, so everything's divided by mass. Now for solids and liquids, let's remember that they're considered to be incompressible states of matter, right? And so what that means is that their density does not change. And if the density doesn't change, that also means their specific volumes don't change, because density is just equal to 1 over specific volume. And so if we're looking at the change in the specific volume here, as denoted by this delta V hat, and specific volume, because these are incompressible materials, the specific volume doesn't change. And that means our delta V term is equal to 0. Because solids and liquids are incompressible. So what we're left with, or just to write it out more clearly, what we're left with is that delta H is just equal to delta U. Ergo, if we think about the constant pressure heat capacity, its definition was that it's equal to the limit as delta T goes to 0 of the specific enthalpy over delta T. But we know from this relationship that for solids and liquids, the specific enthalpy is just equal to the specific internal energy. Let me write the limit. Which is the definition of constant volume heat capacity. And so just to write this out even more clearly, that means Cp is equal to Cv for solids and liquids. Alright, so this is true for incompressible systems. But what about for gases? So the answer is different, right? And it depends on the type of gas that we're dealing with. For now, let's just consider ideal gases. Alright. So for an ideal gas, let's now once again go to not the specific enthalpy, let's go with the molar enthalpy, because we're dealing with gases, so let's divide everything by moles. So I'll put the tilde here. So we have H squiggly is equal to delta U squiggly plus delta PV squiggly. Alright? And so I deliberately pulled in the P into here, right? Even though it's constant, I could still factor it out or distribute it out, right? So it's back in here. The reason I did that is because, we're dealing with an ideal gas. And so based on the ideal gas law, we know that P times the molar volume is just equal to the gas constant times temperature. So I'm going to replace PV squiggly actually with RT. Plus delta RT. So that's what the enthalpy is equal to. So if we go back to our definition for the constant pressure heat capacity, which was this, I could put in a squiggly here because really the only difference between H hat and H squiggly is just units, whether you're dealing with masses or moles, and they could be converted between the two with the molecular weights. But the definitions are still the same. So now we're considering a constant pressure heat capacity, but with units of moles on the bottom. All right. So just want to clear up any confusion there. But in any case, so our constant pressure heat capacity is going to be equal to the limit of delta T as it goes to 0 for squiggly h over delta T. But now we could apply this relationship. Now we have this plus the gas constant's a constant, right? So that will just get pulled out. And what we have instead is delta T over delta T. Clearly that's equal to 1. All right, and so in our relationship, we have this thing, which we know is equal to CV. And then we just have R. Right? So for an ideal gas, the constant pressure heat capacity is equal to the constant volume heat capacity plus the gas constant. So this is one derivation of it. Yeah, this is one derivation of it. And you'll learn more in your thermodynamics classes about a more rigorous and kind of molecular derivation of this relationship.